All right, so 188.
Is 0.01136.
0.011.
11.
Okay, perfect. So 1.1% roughly. All right. Which example was this again? 5.2.4. So if P is this, what is Q? Should be 1 minus 0.011. Which is what, Nicole?
0.989.
0.989. Okay, so before we begin, that's what it says the world is set at. Okay? By the way, Woodmaker is Belgian. And I was like, where are you from? He goes, Wiesbaden. I'm like, I don't hear any accent. I mean, his English was spot on. He goes, well, I was born and raised in Belgium. I was like, so you're ethnic German? And he goes, yes. I was okay, that explains why you have a little bit of a French flair the way you're speaking. But, oui. Okay. So then it says, consider you take a group of 10 children. So n would be equal to 10. Okay? Standard stuff, this first stuff up front. But let's cut the crap and get to where the math is. C. C. Alright? C says, what is the probability, find the probability that none of those 10 children have autism. Alright, you guys are going to walk me through what to do. Okay, so part C says 0 children. So R is equal to 0. Okay. So we're going to set up the equation. Okay, so Px equals 0. Up first is the...
0.011. What?
No.
Oh, what are we, sorry,
It's
10.
Oh, what was that? What was it? Well, first we got to set the combination, right?
So it's 10 to
Yep.
factorial
10 factorial,
over 0
0 factorial, yep.
multiplied by 10 factorial.
10 factorial.
Oh.
See? Oh, we said R in this case was 0, N is 10. Okay, so that's factorial portion. Okay, now we get to P.
That's just one.
Yeah, let's reset this up first.
Okay.
So, yeah, that's okay. So P is
0.011.
to the 0. What?
to the 0 power. Yep.
Multiplied by 0.989 to the 10th power.
Very good. See, Nicole, you didn't dominate stats the first time?
No.
Because you didn't have a teacher like this. That's what I'm hearing.
You're
I like that.
making over that.
That's what I'm hearing. All right, so now we'll go back and do the math. Now, Amy, your portion.
I'm sorry.
This is, yep, that's equal to 1, right? 10 factorial divided by 10 factorial is 1.
Yeah.
0 factorial is 1.
Right, 1 times 1
Yep.
is 1.
So this is all 1. Okay, so 0.011 to the 0 power, Nicole, is?
Oh man.
You don't have to type this in.
1.
Is 1. Because remember, anything to the 0 power is 1. So they see you starting to type in.
Eventually,
Point
I'll
zero
remember.
one one. Go on. All right, now you can use your calculator. 0.989 to the 10th power.
0.895.
Right.
Okay, so we multiply it out. 1 times 1 times 0.89 is equal to 0.895. Okay, and again, this is just rounding error, or sorry, rounding difference. That's all it is. So 892, 895, that's good enough. Okay.
What were we deciding? What was the 10
Out of 10 children?
have autism.
No, out of 10 children, 0. What is the probability? 0
Zero
is
have
10.
autism.
Yep. Okay, so now, next one says, part D says, what if 7 of those 10 children have, what is the probability 7 out of 10 of those children have autism? Okay, so in this case, it'd be probability that X
10
is
factorial.
equal to 7. Alright, Cav, what do we do next? We're gonna set up the combination here.
So that would be, what, 7 factorial?
Nope.
No, that's so 10 factorial?
Yep, 10 factorial, yep.
Over 7 factorial times 10 factorial.
Negative. This would be n minus r, which would be
3?
3 factorial, yep. Now we'll do the p-value. Again, the p-value was, in this case,
0, 1, 1.
yep. And this goes to the what power?
7.
Siete. Alright.
And the cube,
Yep, q in this case is now,
the same.
yep, 0.989, same number as previous.
To the 10 again?
Nope,
Three.
No?
it's to the 3, yep, because remember, it's
Yeah.
n minus r.
Minus 1, yeah.
Yep. That's fair, just keep the equation in front of you, and then you'll just, the more you do it, you'll notice. Alright, so now we'll run back through the numbers here. And sorry, this is a little low, I apologize. Okay, so 10 factorial, 10 times 9 down to times 1. Then we have 7 factorial, 7, 6, 5, down to 1. Times 3 factorial, which is 3 times 2 times 1.
Are you looking for the answer?
Not yet, I'm just gonna do piecemeal across here. 0.011 to the 7th power is what?
Oh, it is 1.948 what?
Yeah.
Did you ask?
You were right,
Oh.
1.949.
Multiply by 10 to the negative 14.
Okay,
Yeah.
okay, perfect. I was like, wait a minute, this should be a big number, like, okay, 1.948,
8, 7.
that's good enough, times 10 to the what?
Negative 14.
Okay,
Wait, where'd you get 10 to the negative 14?
Because it's 14 zeros.
yeah, it's 14 zeros.
Uh,
Because remember, it's 0.01, so 1% to the 7th power. So pretty much you're taking 0.01 times 0.01 times 0.0, it means whoosh, it's gonna get super small. It says pretty much take 1% of the number in front of it. So this means really small number. 0.989 to the 3rd power is what, Nicole?
0.967.
0.967. Okay. Pull the pants up here. All right, we'll go back and do the combination first.
Okay.
Okay, so there's 2 ways you can do this. 7, 6, 5, 4, 3, 2, 1 cancels out. So that would cancel out that. So then you're left with 10 times 9 times 8.
And then 3 times 2 times 1.
720.
720. So the top part is what?
720.
So
Is
720
that not right? 10 times 9 times 8.
Yeah, it should be, yeah.
Sorry.
divided by 3 times 2 times 1 is 6. So now we get 720 divided by 6 times these two numbers.
Mhm.
And what do you get when you do that?
1.16 times 10 to the negative 12th power.
That's a really small number.
So if I didn't have a graphing calculator,
Sorry.
720 divided by 6 equals 120.
Yep.
And I would do 120 multiplied by 1.948 times 10 to the negative 14.
Yep,
Then times 196 is separate.
yep, just do them separate. Yep, exactly right. How I do it is I just take the first piece, so 720 divided by 6, get that number, and then I hit multiply this equals, multiply this equals.
Can I ask you another question
Yeah, of course.
on here? So
Yeah.
when I try to do to the negative 14th power on here,
Yeah.
I don't know how to do that. I can
No,
do
that's
now
fair.
the other one, but not negative.
So what you're gonna do is 14,
Mhm.
so if we do, let's all make it really similar. We'll do 2 to the,
Negative 14. Wait, what did you say? Oh, you hit down here. I'm
Yeah.
sorry, I was, yeah. Okay.
yeah, so plus minus is right, no, that's a good
Okay,
question,
thank you.
that's a very good question. So, 1.16 times 10 to the negative 12th. We are back in Jim Carrey territory, or Lloyd, is it, what's his name of the movie, Lloyd? So this is pretty much equal to 0. It's not equal to 0. 1.16 times 10 to the negative 12.
That's not right.
Sorry.
I got 1.883 times 10 to the negative 13.
That's in the neighborhood. We'll take that.
I did something.
Wait, what did you get?
1.88372 times 10 to the negative 13.
And you did 1.16 times 10 to the negative 12?
No, when I went 120 times 1.948 times 10 to the negative 14 times 0.967, on my iPhone, I came up with 1.883 times 10 to the negative 13. Close. Let's try this. Close.
That's close enough. If you're getting something that's minus 13, that's close enough. Because that's rounding error when it gets on that small. Okay?
When I do 10 to the negative 12, I get 1.14 pounds.
Oh, yeah, we should have. Okay, so,
So trying to do this 1.16 times 10 to the negative 12.
Okay.
Just do 10 to the
Yeah, so-
negative 12 pounds.
so we'll do 10 to the 12.
And then you hit
Minus.
negative. Oh, I thought the negative was first.
Yep.
Oh,
Yeah.
okay.
It's,
Okay.
you're gonna laugh at this.
There's probably instructions on
Yeah,
here.
the logic for between this, which is more how you think, and versus a scientific calculator, it's reversed. So this you would type in 10 to the
Just how you would.
that you would do 10 button 12 minus equal.
It's like German.
Yes. Except there's not enough umlauts.
Question on utilizing the iPhone.
Yeah.
How do I get that E symbol in the
Turn
iPhone?
it sideways.
And if I hit
Are you
E,
joking?
no, it gives you the scientific, but if I was to do
More stuff on.
120 times
Oh, on the iPhone, yeah.
1.94.
Sorry.
8, how do I get that
Calculator's like
E negative 14?
Just doing it so.
It's X, Y.
I tried that and it gave me something else.
It takes it from an S to an E if you turn
Okay,
it
so we'll
sideways.
do this first. If you do this, if you do
Oh, I finished.
And if you do 1.16 times 10 to the negative 12, what do you get?
1.16.
That's coming.
You get that answer.
Yeah.
Yeah, that is
So it's
1.948.
1.16 times.
So if we go in and do, so we take that is just the 10 to the minus 14 times
Yeah, I get
1,
1.16 to the negative, or to the positive 12.
4, 8.
Oh, did I do that wrong?
I'm doing something wrong. It's
And
okay.
then multiply it times.
Yeah.
This calculator
So
is old
I know this
school.
sounds a little backwards. Start with the most complicated thing first,
Okay.
Gotcha,
Oh,
okay.
and then work out to the easier stuff.
So is it okay to put that as an answer?
Yeah.
The 1.16?
Yeah.
And it would not the,
But I'm looking for you to make the next argument.
and what do those ellipses mean?
Ellipses.
Approximately.
Oh, approximately. Yep.
Okay.
Yeah.
So that's the final answer.
Yeah. I'm looking to you to make you get 80% of it right there if you get to some number like that. But I'm looking for the full. Hey, that's nothing.
So is it fair to say anytime we get anything to the negative power, it's approximately 0?
Anything greater than -6, -7, I would say.
Okay.
Probably actually -4, -5, higher.
Should
Yeah.
extend this variance?
Do you guys want to do another example, or do you guys feel comfortable?
Yeah.
Okay.
Well, for me, it's just my calculator.
Or Nicole can just do the midterm and the final.
Yeah.
I have a question.
Yeah, some of course.
About the homework.
Yeah.
It's chapter 5 where we are now.
Mhm.
On page 166, it's number 4. And I don't understand the question, the English question.
Oh, yeah.
The
So,
task, it doesn't make sense to me.
let me go back real
Find
quick.
the following probabilities using technology. What's that?
Just use a calculator, or
Using technology is use the calculator.
so using Excel, using a calculator, however you choose. Your son, if you want to consider your son technology. Boy, get in here and do my math.
No,
that's
figure
a
it out
black
myself.
That is a. Actually, that'd be Kevin. That'd be more Kevin. Boy, get in here and do my math. Do my numbers for me. That sounds pretty army, I think. Doesn't it?
It does.
He says he is. Well, he was in the math Olympics in the States,
Oh,
but
really? That's cool.
I've seen him do math and I'm not exactly.
So it sounds like he's hitting that rebellious 13. He's trying to figure it out.
He's also pretty lazy.
Yep. So he's hitting that phase. He'll figure it out.
Oh, he will. Or he's gonna find himself in a boarding school.
Woo! When he says boarding school, he means West Point.
Oh,
They cost a lot of money.
Yeah.
This guy wouldn't pay for it, but I threaten him all the time.
private schools are expensive in the
We,
nowadays.
we did put him in private school, and it was about anywhere from $6,000 to $7,000 a year.
Wow.
You know
about
what
right.
it costs here?
Yeah.
It's like 20,000 a year for the
Yeah.
God school or for the German school.
One of my contractors in my office, he accepted the contract to come here on the basis that with his contract, his kids would go to the international school.
Yeah,
That
that's
his
20,000
company would pay
at
for it.
least.
Wow.
Yeah, it's not cheap.
That's nice.
I know, cause I work with contractors, obviously, I'm a contractor, and all of them have enrolled in Dodge or international, and it's about the same cost.
They can go
20,000
to
a year.
German schools for free.
But unless they
Well, we can't, as
finish high school there,
contractors,
their
and that's
transcripts aren't
60
gonna go in.
Yeah, they're gonna finish it,
I
he's
know
staying
two
here so they
kids-
can, but
I think that that was.
it was all on the hook,
They were in
it wasn't that they
German
got
school,
into
they
that school.
weren't able to-
Oh, yeah.
It's not easy to get into it. You have to go and interview and tell.
I would send my kids to German school if they don't speak German. So I mean, I had kids.
But they would if they went there.
Yeah. All right. So let's pick up with, so we talked about probability distributions, we talked about etc. This is going to be chapter 6.
Oh, chapter 5 is super short.
And really all I want you to know is how to do that. Just that probability. That's really all I want you to do. All right, so now we're going to talk about continuous probabilities. We talked about discrete, so we talked about probability. We talked about binomial. Now we're going to talk about continuous. All right, continuous probability. Remember, the entering argument, when we begin any of these distribution questions, is the sum of the probability is always equal to 1. And probability ranges from 0 to, One. meaning that we can have the Lloyd 0.00001 all the way up to 100%. Okay, we have a 0% probability, right? Something happened.
And that E means the sum of all?
Yep, the sum of probabilities. Yep.
Oh, so you couldn't move the E to another, like EQ?
No.
Okay,
That is the Greek letter sigma,
yeah.
and it just says sum up all the probabilities, and when you do, it equals 1.
Mm-hmm. Okay.
All right. So first thing we're going to begin with is uniform distribution. Nice little picture here it has. So if you have a situation where the probability is always the same, so no matter what happens, the probability is always the same. Okay, they're not as common as you would think as you reading this from the book. Okay, an example would be waiting for a commuter train, assuming it's on time. The commuter trains on the blue and green lines for Regional Transit Authority in Cleveland, Ohio, have a waiting time during peak hours of 10 minutes. Okay? If you're waiting for a train, you have anywhere from 0 minutes to 10 minutes to wait. Your probability of having to wait any number of minutes in that interval is the same. All right? This is a uniform distribution. So again, whatever you're doing, you have the equal set probability. So for example, when I take the train home, I go to the Hauptbahnhof, I get off the S line, go upstairs, and then walk over down to the U line, and then when I get to the U line at that stop, I'm going northbound out of it. So there you have what? U5, 6, 7, U5, 6, 7, 12, and 15. Okay, so while I'm waiting there, I've got 5, 6, 7, 12, and 15. Okay, it leaves the Hauptbahnhof. So when I come into the Hauptbahnhof, here's the stop. What's funny or interesting, if you go this way, the 12 goes this way, and then the 5, 7, 6, and 15 all proceed that way. So when I actually get there, I can't pick any train. I have to specifically pick this train. Okay, so my example doesn't necessarily fit here. Yeah, kind of, exactly, yeah, right? I mean, because pretty much during the daytime, the 12 does come every 10 minutes. But you also have these other ones, so it's pretty much every 2 minutes there's a train.
Yeah.
All right, but I have to wait for this, and at nighttime there's a 15, on holidays it's 30. So it's 30 minutes on holidays, and it's fun because there's no one on the train except drunks and people sleeping, especially in the morning. All right. Now, if we want to come out and say, yeah, what is the probability of I'll get a train somewhere between 0 and 10 minutes? Well, actually, it's going to be more towards 10, maybe 2 minute interval where it's late. It's always late. Okay? But assuming the rest of them, very similar to this one, it would have an equal probability. Okay, meaning that over some range, in this case we'll say 0 minutes on the x-axis, from 0, let's say 0 to 10 minutes, okay, just like we have with this one, from 0 to 10, we have some sort of probability. And the probability would be up here on this one, on this chart, and what they're saying for this one would be 0.1 is your probability, or 10%. Meaning, right here, that I have an equal chance, or equal probability, no matter if it's 5 minutes, 6 minutes, 7 minutes. Okay, across the board. So if you look at this, it's uniform. Equal, that's a big stress. Okay, uniform means equal probability across the board. No matter what variable you have on the x, whatever your independent variable is. All right, the probability will always be the same. All right, I think last week I mentioned something about, we started talking about areas under the curve, and then calculus and stuff like that, right? This is where it's actually going to start coming in. No matter what distribution curve you have, if we add up the area under the curve, yeah, it always equals 100%. The most difficult one we have is the bell curve, because this never goes to 0. Okay, but it gets close. But you have these little bitty areas, so it's, we actually, like I said, we have to use calculus to integrate that function. All right? Now, if we wanted to calculate the area of this curve, you'll notice it's a rectangle. All right? This is like kindergarten stuff here. Do they do that in kindergarten? The area of a rectangle? Probably in Germany they do.
Yeah.
In America, this is probably like high school.
Fifth grade.
This is high school.
Area considered?
Nah.
Like that?
What was that?
What?
Huh?
It's geometry, whatever that is.
Yeah.
I did that in 9th grade.
Yeah.
Okay,
Okay.
see? Told
Close
you.
enough,
Was that
I
Bolivia? Please tell me that was Bolivia.
No.
Okay, sure.
You failed it?
I had a really bad teacher. I think she left in the middle of the year.
She laughed or she left?
No, she left.
Oh, okay. She's like laughing at you. You did so bad. Ha 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 ha. Okay. All right. Ooh. Okay. So, so two things. We said the area under the curve, and this would be a curve from this point, from here to here. That is the curve. It is a straight curve, straight line. All right. So, if we want to know the area under this curve, we just take this length and multiply it by the width, and we can get the overall probability of the curve, which we said is equal to, yeah. So if we take length times width, that is equal to 100%.
So that's all that's doing here? And then-
Yeah, that's all that is doing here. So this calculus is saying start at negative infinity, go infinity, and add up these really, really small rectangles
Mhm. Oh,
all the
yeah.
way.
Mm.
All right. This is the easy way, and there's you can actually use a calculus equation if you want to actually sum this up. Makes no sense to it. But yeah, this is the same concept as here. We're just adding that area to the curve. So again, now we can use geometry and basic geometry here to help us determine probabilities. Okay, so we can come back and say, okay, well, what's the if this is uniform probability? What's the probability of having a train somewhere between 0 and 5 minutes? Okay, so if I look up here, if I go from 0 to 5 minutes on this rectangle,
50%.
believe it or not, you're right. Okay, I'll show you why. So if we come in here, we can actually cut the rectangle like that. We know the overall is 100%, right? We also know that this rectangle that we have right here is how far long across?
5.
Is 5 times the height up is 0.1. So 5 times 0.1 is, Nicole? Yep. So the probability of waiting for a train 0 to 5 minutes would be 50%. All right, if it's a Deutsche Bahn, it's probably going to be greater, or it's less.
Yeah, less.
Yeah, that's right. The probability of waiting greater than 5 minutes is going to be less. It's greater. Deutsche Bahn's been pretty sucky the last few times we've gone. They've been late a few times. The Swiss, I've noticed, they don't tolerate that shit. They're just like, run over the cow if it's on the train track. Keep going. Swiss don't care. They're very about punctuality. But yeah, we can use this to go in and actually determine. So if I come back and I say, all right, what is the probability? All right, Amy is now standing there on the podium, waiting for the trains, not the 12, the 3, 5, 6, 7, 15. All right, what is the probability she has to wait greater than 6 minutes? Okay,
6 times 0.1.
so we want to know greater than 6 minutes. Okay, what was that?
Is it not 6 times 0.1?
Because that would be, 6 would be from here to here.
So it'd be 4.
I want greater than 6.
Oh, I see. Oh.
Okay.
So in this case, it would be
4.
4 times,
0.1.
which would be 40%.
You
Okay.
said I'd have to wait more than 6 minutes.
Correct.
Oh, okay.
Yep. If you had to wait more than 6 minutes, the probability of that is we come over to the rectangle, put where 6 is, and then shade which side of the square you want. We want this side, so that would be 10 minus 6 is 4. 4 times 0.1 gets me to 40%. Okay? Why do we teach uniform distribution? Because this helps set up the concepts that we're going to talk about next. About area of the curve, z-scores, all that other stuff we talked about in basic algebra. All right? To me, I just definitely see the value of having this. I really do. Okay? So if we, commuter train. All right, so back to the uniform, it's using the same curve we just used. The first example. So I'm going to draw the rectangle back up there. First one, it says a commuter train, this is 611. A commuter train on the blue and green, blah, 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 we just talked about, rush hour. All right, in this case, state the random variable. The variable is the wait time. How much time are we going to wait? 0 to 10 minutes. Okay, that's the x-axis. Part B says find the probability that you will wait between 4 and 6 minutes. Okay, Dill!
You are always late.
I'm here to figure an exam, because I'm gonna go to work in 5 minutes.
Oh, don't worry, it's going to be online.
Oh, it's online?
Yeah.
Cool.
He's like, alright,
Well, good, we'll come over and say hi.
Alright, thanks.
So we can be like, manager, this is one of the rudest people I've ever seen. He was telling me my math sucked and trying to make fun of me in class. I would never do that. Hey, Dill, I'll stop by and say hi. All right. Okay, so in this case it says, what is the probability from 4 to 6? So we come out here on our chart. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we go to 6. So in this case, now he says from 4 to 6.
So it's just the 2, and that's it right now?
Maybe not that. Well, try.
Yeah.
So you cut that slice out there, and then you find the area of that rectangle. All right, so height again is 0.1. The width is 6 minus 4, which is 2. So the overall probability is 20%. All right. Uniform, like I said, it's pretty straightforward. The next one says 3 to 7 minutes. Okay, 3 to 7. Oops. This one says go from 3 to 7. All right, so in this case it would be, the height again is 0.1 times 7 minus 3, which is 4. So we get 40%. Okay, again, we teach this because it definitely shows the basics of what's going to be a little bit more complicated here in a second. All right. Now remember, go back to the entering argument. The total probability is 1. All right. We said probabilities can be between 0 and 1, but then also we talked about this previously. If the probability of A happening, all right, happens, and we said if you take the probability of A not happening, that all equals 1 as well. Okay, so if I come in and say, what is the probability of getting a train ride, waiting for a train, from 0 to 3 or 7 to 10 minutes? Okay, so what is the probability you're going to wait for a train, 0 to 3 minutes or 7 to 10?
30%, 60%.
Yeah,
70%?
okay, that's good. So we know this piece is equal to what?
40%.
40%. So that means the rest of this is equal to,
60%.
so each one is equal to 30%. Okay, just now taking the next logic step. It says again, if it's total equal to 1, if I know this is equal to 40, then not equal to 40 is equal to 60, and each is 30.
So what is the answer then? It's 30?
I said either or, I think. Yeah.
Okay. 30 or 60.
Yeah. Just however I worded the original. I'm sorry, I don't remember what I said. Okay. You guys want to do another example? I find uniform extremely easy. Ah.
Graphs.
All right, so let's talk about normal distributions now. 6-2.
I know you explained it, but how is normal different than uniform?
Remember, uniform.
Happens more often? Uniform is.
Uniform relates back to the actual probability itself.
Mm.
So when we say uniform, we're saying that the probability is uniform.
Mm-hmm.
When we say normal distribution, we're saying that the distribution or the shape or however the probability itself is on a normal distribution. In this case, we're going to define what that is in a second. All right. Again, if you ever have a teacher that tells you, I grade on a curve or a bell curve, say, nope, don't want it. Because that means eventually someone has to fail. All right, someone has to fail in this. They need to grade on a curve. That means usually the upper end of a curve. Meaning that everyone sucks, so let's take that distribution and move it to the right. Okay, if they grade on a bell curve, that means someone's already doing shitty in the class and they're going to fail. Okay?
Which is not good for anybody.
Yeah, it's not good for anyone. So if someone really grades on a bell curve, say, I don't agree with this. Okay? So let's look at the beginning part here. So yeah, 90% of the stuff that you're going to deal with in statistics is going to go back to this normal distribution. Okay? And this is going to be continuous normal distribution that we're talking about. You'll notice even when we did the probability distributions, things look like a bell curve. Yeah. Remember, this is the shape we're going to talk about. But yeah, a lot of them fall and look very similar in shape, etc. So if we look at the two graphs here, I think this is pretty good. This is a really good example to show you something real quick. Normal curves can be tall, skinny, they can be short and fat. Wow, that's body shaming. They are all symmetric. They are all symmetric. Okay? Unimodal, meaning they have one mode. They are centered around mu, the center point. Okay? So that's the entering argument number one. Is that it's symmetric. The bell curve of the normal distribution is centered around the mu, or the the population average. Okay, so if you have a sample, it would be a sample average. Whatever that average is what it is centered off of. It is not centered off the median, and it's not centered off the mode. It is centered off the average. Okay? What they're showing here is two curves. All right? X again is your, let's see, what do we have here? Both have a mu of 100, so that means whatever value is centered on 100, whatever that is. If it's how many, we asked 1,000 people, how much money do you have in your wallet? We found $100 was the average one, okay, or whatever that value represents. So, okay, and then y is going to be, in this case, think of it as like a frequency or a probability itself. Okay, when normally looking at normal distribution, we don't look per se at a percentage. I like to think of it as a frequency, meaning because this represents, if you will, how many data points do you see at 100? So this might be, in this case, 7% of the data, or however they're representing it. But I like to think of the y-axis as a frequency. Okay, it makes sense because if you go further out this way, you're going to see less responses off the center.
And what was X?
The x is the quality that you're looking for, whatever it is, the numerical quality, age, weight, income, capital cities. Olivia?
I don't know.
There's two.
Yes. Oh
Okay.
yeah.
Wow, it's noon. No, oops. All right, again, this is frequency. Just think of it in terms of frequency. That's how it always helped me out. Now, notice what it's saying here is both have a mu of 100, but one on the left has a standard deviation of 10, while the one on the left has a standard deviation of 5. Notice the larger standard deviation makes the graph wider and more spread out and shorter.
Short and fat.
Wait, say that again? Notice the Y.
Notice the larger standard deviation, this one,
Mm-hmm.
makes the chart
Oh, mm-hmm.
wider, more spread out, and shorter.
That makes sense.
Okay? Let's go back, and this is why I kept hitting this into the ground constantly. Go back to the discussion of precision and accuracy.
Mm-hmm.
Okay? If data is precise and accurate, it will look like this. This is what we want.
That's what's most.
That has more spread. Remember, at the end of the day, as statisticians, we're trying to create links between a sample and a population. And if we get a link like this, a good chart, now we can say, yeah, the center's around 100. Yeah, that looks pretty good. Spread's down, that's pretty good. If we come over here, now we go, I don't feel so warm and comfortable that 100 really is the answer.
A lot of error.
Yeah,
Mm-hmm.
because remember, at the end of the day, that's what we're trying to say. Yep, 100 is the answer. But if I come over here and I go, ooh, is it 100? This could be like 95 maybe, it could be 105, etc. So accuracy, precision, yep, we're trying to hit that point and we're trying to repeat it. This is high accuracy, high precision. So the tall curve here, figure 621, this is accurate and precise. This over here is accurate, but its precision sucks. Meaning that because it's got data points out, notice over here, you don't even have a response out here at 80. But over here you have a response of 80. Over here you have a response of 120. You have no response of 120 over here. So that now is putting down in my head that 100 is really the answer. All right? So when we begin looking at it, okay, we look at a typical, what a typical curve looks like. Okay? Again, number one, the hill, the valley, the peak, centered on the mu. And then again, this, again, frequency, this line never goes to 0. Okay, meaning it never touches the horizontal axis. All right. Who's going to run the calculator now, Nicole? Oh, okay, that's good. Amy's like, shit.
I just been checking.
Amy's like, oh shit.
Yeah. Bye.
Be safe. See you Tuesday. All right. So then we have the hill, the valley, and then we have the inflection points and whatnot. The big thing is, again, the curve is under the area of the curve is equal to 1. Okay. So if we go from negative infinity, the valley side, up to the center, how much of the data would we have? 50% of the data. Yep. All right. We'd have 50% of the data. Dun, 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 dun. Hold on, let me get this to. Look at that, using some physics here. All right, so yeah, it's from 0 to there. So then here up would be 50%. If we take a little chunk, if we go from 50 here, the center point, to this point here, we can calculate how much of the area of the curve that is. All right. When I say the area of the curve, another way to think about it is if I start at negative infinity and I go up to center. Remember how I said this represents frequency, right? Meaning I'm going to see more and more around the center point. So if I start at 0 and go up to the center point, what percentage of the data will we have seen?
Oh,
50%. So
amazing.
it won't necessarily be correct, but to help you think in terms of this, if by going from there to there, we'll have seen 50% of the data. Okay, if you go out here to the tail, right here, you can only see 5% of the data, maybe 2%, maybe only 1% of the data. If I come over here, same thing. I'd see 99 up to this point, 99, 99.99, 99, etc.
Can I ask you a question? Sorry to take away from that.
Yeah, that's okay.
When you're reading news or listening to news and you're hearing statistics,
Mhm.
do you try to create a graph that lets you look for standard deviation to see if it's to see that it's a less spread or not? Or you just know because you've done it so long?
So the two things, if I hear numbers, like if they give me statistical numbers, again, I don't know what statistics they ran, it's probably something more complicated than I know. But that's immediate first thing I ask is what's the standard deviation, how they collect the data, methods, everything. I want to know that portion first.
Right, of course.
So yeah, when they say, monkeys given antidepressants have signs of autism. Okay, well how many monkeys was that?
Yeah.
Did you sample 12 people?
Yeah,
One of
like
which was,
response.
yeah.
How much antidepressant did they give them?
Yeah. So for example, the whole saccharin thing, if you guys don't know the whole, they gave, they said saccharin causes cancer. Go look at the original study. They gave those rats more saccharin than a human would ever have in their life. Of course it's gonna cause
In
cancer.
that case, water causes cancer.
Yes, actually, if you ever you ever wanna do something fun,
Overdose on water causes cancer.
yeah, actually you can
Coffee
do,
causes cancer and it cures it at the same time.
What is coffee?
Yeah, they're both.
And chocolate and wine.
you wanna really,
Isn't there still, used to be a warning on cans of soft drinks?
yeah.
The artificial sweeteners that causes cancer?
So there you go. For Simone, I brought up the Deutsche website. Dihydrogen monoxide awareness. All right, again, because words have meanings. It's water. Dihydrogen monoxide is water. Dihydrogen, H2. Monoxide is O.
That's very logical.
Yes. So if this is the German website. I want to see if I can find the English website. So Simone's the only one laughing right now. She's like, ah. While we're all going, what the hell does that say? I need my English.
So, can you not, do you not have translate on here so you can right click and change it?
Oh yeah, it does. I just wanted to.
Oh.
So this is a funny website. You want to get your coworkers to see who's really paying attention. Welcome to the website for Dihydrogen Monoxide Research Division, currently located in Newark, Delaware. The controversy surrounding dihydrogen has never been more widely debated. And so there's some funny things on this thing. I gotta find it.
So it's saying that
What is it? It's colorless, odorless chemical compound, also referred to as hydrogen hydroxide, which that's true. Should I be concerned? Yes, you should. Although the U.S. government and the CDC do not classify this as a problem toxic, it is constituent known in many toxic substances. Environmental hazards.
but are they referring to drowning?
Why have I not heard about this? What are some of the dangers? Oh, here you go. These are good. Death due to accidental inhalation, even in small quantities. Excessive ingestion, gaseous, can cause severe burns. Steam.
Given to vicious dogs involved in recent attacks.
Contributes to soil erosion.
Cyclones
Yeah.
in the Midwest. Hurricanes.
Exposure decreases the effectiveness of automobile
As you take a
brakes.
swig.
Yeah. Wet brakes. What are some of the uses?
Is this legit? Or what is this?
So what they're doing is
Conspiracy?
this. No, it's not at all. This is actually pointing
In
fingers.
the coffee.
it's pointing fingers at two things. Number one, people's ignorance, number one. Inability to stop and ask the question, what the hell is this?
Yeah.
Something doesn't seem right here. But number two, what it's actually pointing at as well is, do you guys remember a few years ago, Subway sandwiches? Something came out and they said, hey, Subway has in their bread a component that's found in, a chemical that's found in radiator fluid, coolant. Sorry, I can't think of the word all of a sudden.
Antifreeze.
Antifreeze, thank you. And everyone's like, oh my god, I can't eat this sandwich, it's got something found in antifreeze. Thinking antifreeze didn't cause anything. But it took one thing and related it to something else, and people go, I can't eat that.
Oh, poor Subway.
So that's what this is doing.
I don't think that was probably worse than Jared.
Yeah, it's true too. But what this is really doing is it's pointing out that if you're gonna listen to this stuff, like insert chemical here, whatever it is, you need to know what you're really reading. Because you're right, if you don't know what you're reading, oh my god, this sounds horrible.
And shampoos.
Formula One race car for those to use is regulated by the Formula One.
Simone, do me a favor, go home. Is your son still around this weekend, or is he back at university? And sit down with him and just be very serious, try not to laugh, and say, son, we learned something in class today.
He probably already knows this.
Does he? Okay. I want to see it as an experiment.
I'll ask him.
Okay, see it, be very serious, and when you come in Tuesday, let's see if we can get him.
So Travis, I'll put it on Facebook and just write, oh my god, next to it.
Okay, that's fair.
And see what people.
Look what I learned in class today. Ooh, see if you can tell your wife, Kat. I've done this with Derek already, and he was kind of like, once he figured it out, he was like, I hate you. But yeah, try it with, just try someone at home or someone you know, a coworker, and see what they do.
I don't know, because then you might be wishing you didn't work with those people. Like, who do I work with? Oh my god.
All right. So yeah, we can, again, words have meanings, knowing what things set up, okay? So when we look at this, we come in and then you're gonna see this. All this says is take the mu and add a standard deviation. So if you have a sample size, that's why I said, we can't just look at a sample average. We need to look at the standard deviation, tell us how spread out things are. If you have an average and a huge standard deviation, you just told me you're throwing a hot dog down the hallway. All right, no luck there, okay? But if you come in and say, I was mean and a super small standard deviation, that's pretty much telling me now that you are trying to park an F-150 in an underground parking garage downtown Stuttgart. Okay, so that's...
So you're saying there's a chance?
You're saying, no, in that case, there is just one chance. All right? Actually, that's a great example, parking a car. And if in America, you have a lot of leeway, left and right. In a German parking lot downtown, we go to Ludwigsburg, where we park in. Like I said, we usually take our Macan up there, and that thing is not a tank, but it looks like a goddamn aircraft carrier. Trying to park in that garage. And yeah, that would be the equivalent. Okay? So, when we look at normal distribution, that's really good right there. So this is the actual equation of the line. Okay? So this line. Printer says the function is equal to 1 divided by standard deviation times square root of 2 pi to the e power, times e to the 1/2 x minus mu over sigma times to the 2 power.
You said it's the equation of the line, and then you pointed and I missed that. Were you talking about the curve?
Of the curve itself. Yep. So the equation of this line is right here. This class you don't need to know.
Essentially the frequency.
Yes.
Okay.
Mm-hmm. Okay. So when we look at it, we get, again, if we go from negative infinity to positive infinity, we get we get probabilities. Just like we did with uniform distribution. Add the area under the curve. Okay? How much of the population thinks that dihydrogen monoxide is deadly? All right?
Is that
Okay.
in here?
Oh my God. The children.
The kids.
Yeah, die Kinder. Oh Lord. Etc. Yeah.
That's only at crossings.
All right. So one of the other things that helps us set the logic for normal distribution is what's called the empirical rule. And this table right up here on page 179 leads into it right here. Just draws it out for you guys. Okay? Normal distribution follows the empirical rule. That's what defines it and makes it normal. All right? So in this case, it says, if I start at mu, All right, and think of it again in terms of counting data. If I just had 100 data points, and I just had to start counting data points, okay? And I come in and I said, yep, this is my data curve, and I start at mu. And if I start at mu and I add and subtract the standard deviation, according to normal distribution, from this line here to this line, right here, the red, I will count 68% of my data. Okay, so just a little over 2/3 of the data will be one standard deviation away. Okay, now remember, hit pause for a second and go back to the picture of the skinny one and the fat normal distribution. Okay, remind you, if we go out one standard deviation, that's what this picture is drawing. If I go out one standard deviation, 10, I see 68% of my data right there. If I go out, in this case, was it 5? No.
That one was 10.
5, yeah, this one's 5, sorry. So that'd be 95 and 105. I see 68% of my data. If I go out over here, now it's 90 and 110. Okay? I still see the same number of data points, but the values themselves are stretched out.
So you're trying to get this then, right?
It's the same. This has the exact same distribution. Okay?
Well, yeah.
The key is the qualities are spread out.
Right.
Okay, so if it's, let's say, height, weight, yeah, weight would be a good one. So in this case, if I said weight, the average weight was 100 and the standard deviation was 5, that means 2/3 of the people in the class would have a weight between 95 and 105. And that sample, that sample would be, hey, with the population. If I come over to this one, it says if I go 100 and one standard deviation gets me up to 110 and gets me to 90. I will still see the same percentage of data, 68%. I will just now see that the weight scale itself is stretched out more.
So it says that please do not use empirical rule except for real tough estimates. What does that mean?
So what the best way I can describe it is this. I like to use this as kind of a rule of thumb. All right, kind of like nuclear warfare. All right, I can get it in the park. That's close enough. Okay, I don't have to get it on the exact block, street, or whatever. I just need to get out Warhead within a few miles of Stuttgart. That's good enough. Okay, back in the Cold War, the Russians sucked at targeting, so they made their bombs bigger because they knew they could never hit the target. So, but if they could get it close enough and they had a big boom, it would do the work. We had smaller booms and we could hit the target, which means a lot less collateral damage. All right. Same logic here. I just use this kind of rough, because again, your samples are never going to fit this curve exactly. It just helps you get it in the ballpark. Okay? So now if we go out 2 standard deviations, we will see 95% of the data. Okay? We're going to talk 95% over and over and over in this class. Confidence intervals are 99 times of the time, most of the time they're at 95%. We'll talk about confidence intervals next week on Tuesday. 95% is kind of the go-to number that we use in statistics. All right, so be careful. Like it said, remember the maximum probability can be 100. So if you can calculate 100 minus 99.7, 0.3, you will see that for both ends together of the curve. Translated, that means for the 3 standard deviations here, 0.97, we go for 3 standard deviations, that says that we have that 0.03 left over that's not included. Okay? And that means it's split between the 2 tails. So half over here, half over here. We come back up to the 68%. The leftover in that case is 32%. So that means 32 divided by 2 is 16. That means 16 is left over here, and 16 is left over here. I'll draw that out for you guys so you can see it. So if this is 68%, all right, that means what's in red is equal to 32%. But this is equal to 16, and this is equal to 16. Okay, that's all that's telling you. All right. So now the question is, we want to find, just like we did with uniform distribution, probability distributions, now we want to start asking questions of, okay, let's say we'll go back to the tall and skinny chart all of a sudden, okay? We said mu for that was 100, okay? Let's say someone comes in and says, okay, well, what's the probability of someone being less than 95 pounds? Off of that chart.
Off of them.
Where mu is 100, standard deviation is 5. What are the odds, what is the probability someone is less than 95 pounds?
And where is 95 on that chart? Is that to the far right?
So if we went back and looked at it,
That's what I know.
tall one, here at 100, one standard deviation out was 95. That's probably not right. It was about like right here, if I remember right. Okay? We want to know what is the probability of someone having a weight less than 90 or equal to 95 pounds. So that means I want to know is what is the area under the curve from there to there.
5?
Nope. Because remember, this is quality. Whatever that quality is, pounds, age, dollars, etc. The area under the curve is equal to 1. We're going to come back, and this is what we're going to do, show you how to calculate this. Okay? That is where these come in. Z-scores. Right there on the board. And we'll talk about T-scores a little bit later. I'm just writing I'll write them both up on the board right now. All right, empirical rule is approximation, blah, 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 but if we really want to calculate what that probability is, we need to use something called a z-score. That'll translate to a p-value, kind of like what we did in basic algebra. All right. In this case, we look at z, we'll translate what everything is saying here. Z is the actual score. X is the actual like characteristic or number or test value. Put test value. Mu is your average. And sigma is your standard deviation. All right, so we'll look at the first one here. First one says, example 631, says, the length of human pregnancy is normally distributed with a mean of 272 days with a standard deviation of 9 days. Okay? So it says I have a bell curve, a normal distribution, and it says on average the mu is 272 days. Okay, so step one, draw a bell curve. Always draw a picture. All right. And then it says the standard deviation is equal to 9 days. Okay. Part B, where it really begins, says, find the probability of pregnancy lasting more than 280 days. Okay? Lasting more than 280 days. So what we're going to do is we're going to come up on our chart. If the center there is 272, we know, according to this, 280 is to the right of center.
Mhm.
So we'll just arbitrarily put 280. We don't know the scale, but we're just going to put 280 somewhere about right here. I'm going to draw on 280. Something like that. Again, it doesn't have to be perfect. And then go back to what it says. It says, find the probability of pregnancy lasting more than 280 days. Okay? So, remember the uniform distribution?
Mhm.
When I said, what would be the probability Amy would wait for a train greater than 6 minutes?
Mhm.
We shaded in the square to the right.
Mhm.
So in this case, we would shade the curve into the right. So what it's asking, just like the uniform one, we need to know what is the area under the curve for this.
So just doing the length times the width?
Kind of. We have tables that will tell us that when we get there.
Okay.
I'll show you in a second. First, we have to calculate z. So step one, draw the picture. Put everything on the chart. Give yourself a representation. What am I looking for? Okay, step two, now I'm going to go in and use my z-score. Okay, z is equal to x minus mu over sigma. X is test statistic. The test number, test value is 280
Mhm.
minus
0.
272, our mu, all divided by 9, our standard deviation. All right, 280 minus 272 is 8, divided by 9, gets me to what?
0.89?
0.89?
89.
Oh, okay.
Well, it's a lot of eights, I just went to 89.
Oh, okay.
Yeah.
I'll put 8 repeating. There we go. 8 with a hat there means repeat. Okay. Step 2, calculate your z. Alright.
Step 3. Oh, no.
Step 3 is now we're going to use the z to find a p-value. Alright, because it's integration, someone's made a nice little nifty table for us that we just go in and calculate what that is.
How do we find the p-value?
That's what I'm trying to pull up the table. One second. Give me 1 segundo. Dun, dun, dun. All right.
That's interesting, the answer in the book, because are they doing the same thing we are?
Mm-hmm.
Yeah.
They've got a different number, they got 0.187.
I think that's the p.
I think that's it, is the p-value.
Okay.
And that's what we're trying to
And
find.
We're supposed to use this to calculate it?
What I will do is I'll provide you guys I thought the table was here. It wants you to do all this in a calculator. I don't want you to do this in a calculator. This is the one thing I want you to do by hand. So what I'm going to do is I'm going to come in here and I will put this on the website so you guys can get to it.
And it's supposed to be in here?
Yeah.
Is it a
I don't want. No. It's a way to tell it to speak English. No. Shit. Okay, so let's talk Z charts. And believe it or not, I think this is the one.
Is this it?
Yes, those are the Z charts right there.
You wanna borrow it?
I'll put this up on the screen if I can get.
Area from mean to Z?
Kind of, yeah. Alright. That didn't really help.
You can do shift and then scroll.
Oh, that's right. Yeah, that's right. Okay, is the picture that it's. Kind of hard to see. What I will do is when we take a break here, the office is open. I'm gonna print out tables for you guys. There should be in the PDF. It should be there as well. Let's see if I can find a better one.
So you don't have to memorize this?
Nope. Oh, you can go to ztable.com. Wow. Z-table, yeah, Z-tafel. Come on, German internet, let me have the thing I want. There you go, thank you. Just yell at it, see?
It's a weekly site.
All right, so this looks like a mobile build. Oh, that's right, I got zoomed in, that's right. There we go. So Z-table, and I'll put the link up so you guys can go to this. Okay, oh, and you can get an app if you want. Okay, so we look at the chart there, the table it's given us, okay? And it says these table entries equal what starts out if we go from negative infinity up to the Z value. That is the entering argument here. Okay, so if they have a printable one, I'm gonna see if I can print this puppy out and get to it. Okay, so negative, so in this case, table entries for represent area under the curve from the left. Negative scores in the Z table correspond to values which are less than the mean. So if you have a negative Z value, it's the left of the mean. If it's a positive Z, it's to the right of the mean. Okay, so now we get into the actual charts themselves. Okay, so these are the negative ones. Z is negative, you'll see over here on the left. And I don't want you, Weebly. And these are your positive Z's. Okay. Oh, and you can actually, wow, this is actually pretty cool.
Excel?
Yeah. You can actually get some things for Excel here. Peak value calculator, that's pretty cool. Shows you examples, how to do it. Wow, this is actually pretty dang cool.
Z-score table.
Yeah. Calculate your Z for you, just to give you a, wow, this is actually a pretty good website.
Yeah, right?
Yep.
Z-table.
Yep. All right, so what I want to do is
It's probably built by some college kid.
probably some kid who got bored.
Bradley built it.
Yeah, probably. He was probably like, well, I got bored one night and I just built those. He came to class last night. He walks in. I was like, aren't you supposed to be in France? He goes, we're not going tonight. We're leaving tomorrow. And I'm like, ugh.
I still can't believe his parents are taking him with him, forcing him to go as an 18-year-old adult.
I know.
Yeah.
I'm not quite there as a parent yet, so I guess I can't understand.
Oh, I would be. At 14, I'd be like, stay home. You're good.
They must not trust him.
I guess not, yeah. My wife would be the same way.
We don't want pregnant.
All right.
We don't want a
Good now. So, So two things here. Number one is, so here is a Z chart. Remember, these are the negative Z's. This does not have the picture of the chart with the table. Remember, if it's negative Z, it looks like to the left. It looks like this picture. So these are negative Z's. Remember, it looks like this. The Z is on that side of mu. Okay? So if we go back to it, we'll explain the table here real quick. All right, so two things for the table. The Z value is on the exterior of the table. Okay? Z, and then the enter is your P value. Okay? The P value. So for example, if I give you negative 2.00, okay, first we come to the column and we find negative 2 point, that first number. Now these tables, you can kill the messenger, they used to confuse the hell out of me too. So if I give you this number right here, or 2.07, negative 2.07. First I gotta go down the column and find negative 2.0 on this column. And then on the row, first top row, I'm gonna go over until I find 0.07. Okay, so if I want negative 207, I'm going to have negative 2.0, and then I will scroll over till I get 0.07. And now we're going to play a big game of, can my fingers find the right area? So my corresponding p-value is 0.192. So that means if I start at negative infinity and go up to a z-value of negative 207, I will have seen 1.9% of the data.
So we're saying the Z is negative 2.07.
Afer. Yep,
So
I'm
for-
sorry.
For our Z, it's 0.888.
Yep, I was just doing an introductory, showing you how the table works. All right, so now, yeah, we'll switch over to 2.88.
So this
Or,
chart doesn't.
sorry, 0.88.
Doesn't, I don't think.
And I'll
this is
explain
right.
why.
Okay.
Because yours goes off the center.
Well, it doesn't have any negatives, but
It
yeah,
Goes off the center. Yep, I hate those tables.
And we're not looking at some, yeah.
That's why I like to have a negative and a positive table.
Okay.
All right.
0.888.
So now we're, yeah, we want to find 0.88. So we have to find first 0.8. And now I'm going to go over and get the 0.08. So this is down to your tenths, and this is filling in your hundredths.
So it's 0.8106.
So to explain that, if I look at this, I want this is the tenths, that is the hundredths location. So this is the same thing as 0.8 and 0.08. Getting me down to that, which would be 0.88. When I do that, 0.88, I get 8106. 8106.
And that's the data.
That's the P. right?
Yep. So that means my p-value from the table is 0.8,
Oh, shoot.
what did I say, 106. So,
And that's the probability? Is that, what was P?
so that tells me, again, if I start, that's why I draw the picture, and immediately go back to the picture. Okay?
So that was the probability of pregnancy lasting more than 280 days?
Nope.
Oh, no.
Not lasting.
So what we have so far
I don't think
is
we-
negative infinity up to that point.
Okay.
Okay? So what we calculated was actually this part of the chart. So this part of the chart, because remember, these tables are built off that picture. Negative infinity to that value of z. So if I look back at here, we used a positive z table. That is what we calculated. See this picture?
I think we need the other side.
We want to know the opposite side of this. Okay, so if what is the odds of a pregnancy lasting up to 280 days? 81%. but we want to know greater than 280. So now we just come in and go 1 minus 0.8106, and that gets us to,
19%.
yeah, roughly around 19. That's close enough. Okay, so when we first started and I did remember the sum of the probabilities equals 1, A and not A, always remember that. Because you have to ask yourself, what am I looking for?
Right.
Go back to the pictures, remember what the tables are based off of, and set it up appropriately. Okay, the next one, right underneath it, if I remember right. Next one says, find the probability of a pregnancy lasting less than 250 days. Okay, so step 1, draw the picture. Again, I think the pictures always help. All right, so 272 is in the center, 250 is to the left. Standard deviation is still 9. All right. Now we need to calculate a new z-value. Z in this case is equal to 250 minus 272 divided by 9. Do that math, I got minus 2.444 repeating. All right. All right, so now
So that's our z values.
that is our z-value. Step 3 now is to go to the table and get my corresponding p-value. So it is a negative z. So before you even look up anything, because it's a negative z, the number should be less than 50%. Okay?
Yeah.
Out of the table. All right, and we want to know this portion of the chart. All right, so now we're going to take negative 2.44, negative 2.4, and over to 4.
0.0073.
Yep. So my corresponding P is 0073 or
That's right.
0. There's an extra 0.
0, 0.
Yep.
So is that PX or is P?
Oh, it's PX. Yeah, sorry.
And that's a probability of less than the amount of days.
And that's why you want to go back now and reread it and make sure, is this what I'm looking for? It says, yeah, what is the probability a pregnancy will last less than 250 days? Which is, what is that, 8 months? 8 months and 10 days? So that would be roughly, 3 weeks early? Okay. Yep, do the math, less than a percent, sorry. Less than so it's pretty far out there. Remember, your scale might not be perfect, but it gives you an idea.
That's what, 0.73?
Yeah, 0.73%. So if something about according to this, premature births are not that common.
So our answer here would not be the 0.0073, we round it up and go
percent.
I'm sorry, we
Yeah.
changed it to a percent.
It would be 0.73%.
Right.
Yep. A firm.
So, question,
Yeah, of course.
this may have nothing to do with it. How would we determine the percentage between 250 and 272?
Ah, very good. Okay. So what we do for that was going to be one of the problems. But so there you go. You guys can calculate it. I'll just tell you how to do it, then you guys calculate it. So again, go back to the uniform distribution we had. And I said if we go from 3 to 7, we can cut that chunk out, right? And or we could add up this square and subtract them both. Kind of the same logic here. If we want to know what this area in the middle is, I'll paint it red. In order to do this, if I take the z up to here, which is 50, and I subtract this portion, smaller portion, I will get what's left over.
So would we do the z-score for 272 and then get our p-value for that and then subtract those two?
You'd be subtracting the p-values, yep.
Ah.
So in this case, if you take this, we know this is 50%, so it's pretty much looking like this. You would take that right there, which represents 50, all right? Then you would go in, determine what this is, and then slice it off. So that when you're done, did I do the blue one in my pocket? No. When you're done, you only have that, what you're looking for. Okay? So, so here's the thing. If you know that the p-value here to the left is equal to 0.0073, the p-value of half of it, the half of the curve is 0.5. Take 0.5 minus this, and it gets you to the intermediary. So if you do that 0.5 minus 0.0073.
4927.
Yep.
And that's our p-value for that.
The leftover part, yeah. So that's pretty much telling you you're 49% points away from the center. That's pretty far away. Because remember, one standard deviation is 34% away. Go back to the empirical rule. 68% both. If we go out one on one way, it's 34%.
32.
No, 68 divided by 4, 2.
34.
It's 34. More you had me there.
Sorry, yeah.
No, you had me. I was like, oh my god, am I wrong? But yeah, so that'd be 34%. We're now, this is 15% points more. Actually, if we look at the next one up, 95% is 42%. Remember, go to the next step out on the empirical, about 2 standard deviations, that's 95%. 95 divided by 2 is what, 40 something?
2.5.
Yeah, 2.5, 42. This is actually past 2 standard deviations. So we can also use Z's and P's to tell you how common is this. That's another reason we use this. We go, yeah, it's 40 percentage points away from the center point. Oh, compare it to the empirical rule, it's 2 standard deviations away.
Wow, so it's a lot.
And now you sit here and go, wow, that is a lot.
Initially, it doesn't seem like.
Yeah, it doesn't seem very much, yeah. So when we do, so that's why when we originally started, and everyone was asking me questions about standard deviation, I said, yeah, you have to put it into context. Standard deviation and z-value helps us put these things into context. Okay? So the further it out, again, we go back to the further out it is, can you say that, is this common?
What's the
No.
further, the more standard deviation?
Yeah.
No.
It doesn't seem.
Yeah, this is not very common. Is it going to happen? Yeah, it's less than a % chance of happening. It's not a Dumb and Dumber chance of happening.
But with 9 being the standard deviation, 9 days, the standard deviation out of 272 days, that's definitely less than 10%.
Yeah.
So that would be a tighter shot.
It's pretty tight. 9 days is pretty tight. How about this? You guys run the number, just a z, change this to 15. Just real quick, just calculate it. if the mu is 272 and the standard deviation is now 15, run the z for 250.
Wait, mu is 272 and what was the other?
The sigma is 15. We're just changing the sigma, standard deviation.
So the x is still 250?
Yeah, it's still 250. What happens to the z value?
It drops a whole point.
It's negative 1.46.
Okay,
Negative 1.46.
negative 1.46. Okay, so now we'll go to the z table and find the corresponding p. Negative 1.46,
Mm-hmm.
46.
0.0721.
Yep. So by increasing the standard deviation by 6 days, the corresponding p-value for that, so we kept everything the same except for the standard deviation.
No.
The p-value went from less than 1% up to 7%. Meaning that, notice, the standard deviation got bigger, meaning that this sounds more common.
That's weird.
No, it's not weird.
No?
You stop thinking about it, because remember, go back to the skinny and fat.
Yeah.
Skinny, we had a skinny chart, we just made it fatter. So the height shrinks, and now we're less certain about mu being 272. Because now we're saying, yeah, preemies at 250, yeah, 7% of the time it happens. So what in 1, with a tight standard deviation, was really, really rare, now is very common in bigger standard deviation.
Still 7% is not
Yeah.
too bad. My son's
Oh, was he? Okay. How young was he?
about 6 weeks premature.
Oh, wow.
My wife had every issue with pregnancy you could possibly have.
Oh, no bueno. Okay. All right. You guys need a break? We've been sitting here for about an hour and a half. Can stretch your legs.
What time is class over today?
My goal was to get through the rest of this chapter,
Okay.
so probably better 1:30. I'm guessing like 1:30. I just wanted to zoom through
Oh,
this.
it's a long chapter.
It is. That's why I was hoping we'd speed up. We'll see. Etc. Again, I would rather have you know it versus and understand the concepts. And then when we get to the end, you're like, oh, I have no clue what the hell's going on. Z, what is this Z thing? So yeah, take 10 real quick, get up, stretch your legs. I'm gonna go pick up my sword. And then I'm gonna put the Z, when I come back, I'll put Z table in. The website, that is actually a good website.
Actually, I'm gonna run and get the 2 water jugs and get.
Okay. Do that. And yeah, if you put it in terms of that uniform distribution, this Z stuff is pretty easy. Like I said, just go back to that, draw the rectangle. And then when you draw the rectangle, same equivalent. Just think in those terms. Yeah. It's just, I know we get the table and all the, that's what gets really confusing. When you guys come back, we'll work on, how about this? We'll, number 4 on page 187. That's what we'll work on for a few minutes.